So good afternoon, everyone. So thank you for coming. So I'm Feilong from the Meta, and today I'm going to talk about the organization we added in Meta for Presto in the next 10 minutes. So I will first give you an overview of the organization we added, and also I'm going to go into the detail for 3 of them in the talk. So currently in Meta, we are focusing on adding query rewrite organizations. This is because these kind of organizations can benefit both Presto Java and Prestissimo, which is the future of Presto. And also, all these query rewrites, they are motivated by the production queries we see, and also they are targeting the suboptimal plans we observed in the production queries. So one of the first organization I want to introduce is the organization which we introduced to mitigate the skew in outer join. So all we observe in our workload is that for some of the outer join, a significant portion of join case can be null for some of the queries. And this can be very bad. It's because all the nulls will be hashed to the same value, and all these keys will be processed in one single worker. And this will lead to significant workload imbalance for the whole query. So what we did is that we're going to rewrite this query so that the null value is going to be converted to random non-null values, which will never get a match. And this is because the null key will not get a match. So what we did is that we are going to use a combination of a coalesce, cast, and random function to create a new join key for this query and do the join on this new key. So maybe I think I can show an example to make it more clear about what it does. So there are 2 tables here, and we are joining on the key. Here we can see that we have many nulls on the join key for the 2 tables. And when we do the join, we're going to have all the null keys sending to worker 1 for evaluation. And this will be very slow because we are going to have worker 1 executing most of the work. So all we did is that we're going to create a new key, which is the K2. And in this new key, using the previous query rewrite, we're going to convert the null key to some random non-null value. And by doing this, if you can check, we are adding a prefix L and R on the new key so that they're not going to match each other when we do the join. So after we do this organization, we are going to have the workload distributed evenly across all the workers. And so this is the number we got from our production queries. So for some of the queries, we observed that the latency improved from 11 hours to only 4 minutes because they have huge skew. And also, this organization is now integrated with a history-based optimizer, which means that it can turn on by itself with the history of their query. So the other organization we do is to optimize the cross-join to equi-join. So in Presto, the join with non-equi condition is evaluated with a cross-join followed by a filter. And this cross-join will be evaluated with a broadcast join. And the problem is that if the build table size is large, then maybe we are going to see out-of-memory error for this broadcast join. And even worse, the cross-join will produce huge intermediate output, which will be processed by the next stage. So based on this observation, we introduced 2 rewrite organizations to convert the cross-join to equi-join for our workload. There are 2 patterns we target. The first pattern we target is array contains in join condition. The second one is all in join condition. So let me go over the first pattern. So the array contains is a pattern where we have 2 tables, T1 join T2, And in T1, we have one column which is an array, and T2 is a column of a K. So the condition is that when the array contains data on T2, it's going to be a match. So what we do here is that we are going to unnest the array to produce a new column. So and the join will be on the unnested element with K on T2. So this is because if there's no element in the array which match the K on the other side, then after we do the unnest, there's still no match. But if there is any match on the array, we are going to have a match when we do the unnest. And also notice that we have array distinct function here, because if there are duplicate matches in the array, we don't want to output multiple output rows. And this is an example of how we do this. So we have T1 and T2, and we have array on T1 and K in T2. So we do the unnest, and the element in the array will be unnested as a new column as element in T1. Now we can do a join with T1 with T1 element and T2K, so that we are going to have an equal join rather than a cross join. And this is from a production query we have in our workload. So we can see that before. So the above picture is from the before the optimization. So before that, we have a cross join. So with only 11 gigabytes of data, the output of the cross join is 17 petabytes, and the query just died at this time. So, but after this optimization, after we process all these 62 gigabytes of data, we only have 400 kilobytes of output for the inner join. The other pattern we target is the join with the or in join condition. So this is the query where we have multiple Ks and we have multiple equal condition connected with the or. So for example, in this one, we have T1 K1 equal T2 K1 or T1 K2 or T2 equal K2. So the idea of this rewrite is a bit similar to what we have in the previous slide. So here we also do the unnest, but we are doing the unnest on both sides. And here what we are doing is that we unnest an array of index. And the index size is the same as the number of equal conditions we have in the join in all clauses. So in this example, it's unnest array 1 and 2. So, and we're going to get a new K based on this unnested index. So this is the example. So for T1 and T2, we're going to unnest it. And here, we're going to add one more column. First is the index, which we got from unnest, and it's 1 and 2 in this example. And for K3, we're going to have like a value of K1 if index equal to 1. And K3 will have value of K2 when the index is 2. Now we can do the join with T1 K3 equal T2 K3 and index on the two sides. And also we are going to have to do some filter later, but I omitted here for the for simplicity, and you can find in the open source implementation. So the last optimization I want to go through is the payload join. So payload join is the target the pattern where we have a left join between one big fact table and multiple dimension tables. And in this optimization, we target the dimension tables which are not small enough for broadcast join. So in this case, we're going to have the left join to be partitioned. And the fact table often contains large columns like map, array, or row structs, which we call a payload here. So because we have multiple joins, these payloads are going to be shuffled during the partition join. And the idea we have here is that we want to get rid of this like parts of the payload and join the case first. So let me show you with a small example. So here we have two left joins. And the yellow part is a map and array, which we can have even more as the payload. And we have two dimension tables, which is which have K1 and K2. And in our workload, we have observed like joined with, queries with way more than 2 level join. I only show 2 of 2 here. So when we do the join, we can see that the payload is passed through the joins. However, with this organization, all we're going to do is that we are going to join only the keys on the effect table. We're not going to pass the payload here. And all we do is that in the very end of the join, we're going to do a write join to attach the payload back. And by doing this, we avoid passing the payload across the multiple join and only do it once. So for all the orientations, it's available in the open source implementation. You can find it in the repository. And also, I want to thank my teammates Srini and Mulana who contributed to this orientation. So thank you. Yeah.
How do you decide what query plan shape to optimize?
For these for these 3 organizations, I think for some of them, for example, the null sort, we call it null sort, it depends on the distribution. So previously, what we have is that we just manually turn on for some problematic queries, but now it's based on HBO. And for some of the others, so it's more about we are trying to move to HBO to have it turned on for this. So, basically they have they target a specific pattern, and the challenge is how do we identify these patterns. And the challenge we want to solve now is by HBO.
Yeah,
so yeah.
What patterns are used the most, right, for your production workloads, for example? Yeah, like that.
Oh, you're asking which one is the most common one?
How do you decide what is the most common and then focus your effort on optimizing that?
Oh, we're going to do some analysis on the query plan. So we're going to the offline analysis. Yeah, offline analysis, yeah. Yeah.
What kind of tools do you use for result verification when you?
I think Presto has the Presto verifier, which is part of Presto. So yeah.
In your first slide, you talked about optimizing from 11 hours to 4 minutes.
Yes.
So what is the maximum runtime of those queries at Meta?
We do have some limit on the. For some time limit on some people we don't want to have some bad query to keep holding the machine for a long time. But I would say that we have a limit, but I don't know if I can give the exact number. Sorry. Yeah.
Sometimes there's more than one value. Let's say null and maybe a 1 is a lot. With that implementation, actually, we name all of them. So let's say a null and a -1, right? Let's say those are majority pattern of the data.
Yes.
So you replace all of them.
For the null, yes, we are going to replace it with.
There's another value that's kind of equal amount, close to it, right? Would that be beneficial to also rename those values, not just null?
So the reason why we do null is because null always get no match. So but definitely with some you mentioned about the 0 or -1, which are also common valued with skew. So yeah, for this we may need some more trick in the rewrite, because actually 0 or -1 can actually match something. So but now you always do not match. Yeah.
How does that compare to just adding a filter is not null before the join?
This is for outer join. For inner join, you can get rid of the null, but for outer join, you cannot. For outer join, the null may produce output on the outer side. So you cannot simply filter the null. That's why I'm saying that it's targeting the outer join. For the inner join, you can just filter the null. Yeah.
Which approach do you use to test this, so that you don't miss any scenarios? You create this rewrite, and then this rewrite push to code, and then in code you have many queries. You might miss some cases. How do you release this?
What do you mean by miss cases? You mean miss some cases which can benefit but not benefit, or? Sorry? Oh, testing. I think like we have like Presto has the verify test. So like PT verify is one part of the Presto open source. So like you can use this PT verify to do the testing, like compare like two queries with and without optimization. Yeah.
And do you use this?
Yes, of course. Yeah. Okay. Okay. Yeah. Thank you.